So this is a little bit different than some of the topics we've been talking about earlier today. We're going to be talking about RIST, the Reliable Internet Stream Transport. This is a new specification from the Video Services Forum. I'm sure Ciro will give you a little bit of background information about that. But this is an interesting look at its performance on networks that have errors. And basically, RIST can apply to any type of network flow that uses RTP. So it is highly applicable to many of the things we've been talking about. So looking forward to this. Thanks, Ciro.
Thank you. All right. I'm Ciro Noronha, Director of Technology with Cobalt Digital. And here's what I'm going to talk about today. We'll tell you about why RIST. We'll give you an overview of the protocol, technical overview of the protocol, and then we jump right into performance measurement. And we're going to look at the packet loss performance and packet reordering configurations. The output of that is how to fine-tune a RIST link, and I'll also tell you about some demonstrations we did at, for multi-company operation. So that's our motivation here. So with the advances of compression, the bit rate required to transmit video has gone down, and the internet infrastructure capabilities are going up. So you can use the internet as a low-cost contribution link. However, the internet drops packets. So you got to deal with that. You got to recover those packets back. So you need a protocol. This is not new. You can find solutions like that in the market for many years now. But they are all proprietary. They are sandboxes. If you buy the sender from one company, you got to buy the receiver from the same company. Now, the Video Services Forum then decided to take a crack at that, at the urging of the broadcasters. They basically said, hey guys, fix this. Put your house in order, right? I want to mix and match. Y'all doing the same thing, do it the same way. So we started this, the VSF started this activity group in early 2017 to solve that. We're not inventing anything new, we are making a common specification. The RIST Simple Profile was published in October 2018. So about a year and a half after we started, we had a first publication. So, packet loss recovery. The technique used in RIST is called ARQ, Automatic Repeat Request or Query. And this is a name for a number of retransmission strategies that used in the face of packet loss. TCP uses some of that. And it's pretty simple. It's basically, if I don't hear anything from you, everything is fine. But if I've dropped anything, let me know and I'll resend it. The RIST protocol uses ARQ. So let's look at it. Let's see how it works. You normally have a sender and a receiver and buffers. The sender transmits the packets and saves them for possible retransmission in case they are needed again. So let's say that this packet here is lost. The receiver has this much buffer to take care of it. So it sends a request saying, hey, I didn't get that one. How does it know it's lost? Because of sequence numbers. The sender still has it and sends, here you go. But let's say it's lost. Lost again. So how long does that take to determine a round-trip delay? So a round-trip delay, after that, if the receiver doesn't see the retransmission, it says, OK, send it to me again. And since I am running out of space in my diagram, this time it's going to work. And it made it just in time for it to get played. So that takes another round-trip delay. And of course, you can retry this multiple times. If I had another screen here, I would have done it 2 more times, right? But I don't. So let's take a look at the protocol basics. Let's look at the sender first. The primary stream transmission is through RTP, using the relevant standard. So that gives you baseline interoperability with RTP implementations. So it is SMPTE 2022-1 for transport streams, and you send UDP flow to you send basically UDP packets to a port that's chosen to be an even number. You also have to send what's called RTCP, which are control packets. And they are sent to the next port up, and the primary function is to establish state in firewalls. So I'm going to leave that hanging because I have a nice picture for that later on in this presentation. And that other stuff, what you put in the packet, you only bother with that if you're actually writing the protocol. And I don't want you guys to fall asleep on that. So what happens in the receiver? It needs to listen for the RTP flow on port P, and P+1 for the RTCP packets. The receiver will send periodic RTCP packets towards the sender. And they are sent basically to where it came from. So again, this is to create state in firewalls. So the firewalls will treat that as a response to the sender RTCP and will allow them through. Okay? If the receiver has packet loss, it will send a retransmission request as an RTCP packet. Let's look at this retransmission request. What do we do? What kind of requests we can make? Those requests are built using what's called compound RTCP packets. You don't need to worry too much about that. But essentially, it's a NAC. I didn't get it. I didn't receive this. So in the RIST group, we define two types of NAC messages. One is called the bitmask message. That's something we reused from our RFC 4585. And it basically can request any pattern of the last 17 packets. It's good for salt and pepper kind of loss. And then we also standardize the range message, which basically asks for a block of packets. So implementers can use one or the other, and a very smart one will make it even adaptive and see which one is better for the loss you're talking about. How do we send a retransmission? A retransmission is an exact copy of the packet. Obviously, it has to have the data because you didn't get it, right? We send it mixed in with the media on the same RTP flow, but we need to differentiate that from the original packet. So you need to be able to tell whether a packet is a standard original packet or retransmission. Why? Because of this system stability. You don't want a retransmitted packet to be the anchor for you to call packet loss. So what in the RIST group, how did we do this? We used the SSRC field. We co-opted a bit in there, and 0 is original packet, 1 is a retransmission. Okay? The point here is that helps with system stability. Now, my pretty cool animation, pretty proud of this one. I'm going to show you how it works over a firewall. You have a sender, you have a receiver, and they are all usually behind firewalls. Usually at the sender side, unless your IT department is really paranoid, you don't need configuration on the sender side because it's going to send something out into the internet. On the receive side, your firewall needs to forward P and P+1 to the receiver. The sender will just transmit to this public IP address P and P+1, and this guy will just listen to P and P+1 on his side. So let's send some video here. Okay, there it goes. It gets there, because it's forwarded here. Okay, what about the control packets? You know it's going to get there too, right? Now, but it's now purple. It got here. Because, again, I forwarded the port. But since I forwarded the port, I can write that state back. And, yeah, see, he likes that. He likes that. So this is the response. So this thing works really nicely over firewalls. And, I mean, we have it working, right? Additional functionality, bonding support. What's bonding? Bonding is, we have support for bonding in the simple profile. And Bonding is simply you split the stream over multiple physical links, so you can use the bandwidth in parallel. The receiver can send the next on either one of the links, or I don't need to say either, any of the links or over the paths. And you can also use this for redundancies, just like 2022-7 seamless switching. You can send 2 or more copies over different paths, and the receiver will use whatever packets it got. If it may not, it's unlikely that the same packet gets dropped over the 2 links, right? Or 3. So, but if it happens, we have next to deal with that. So what we need to do is reserve a part of the buffer for reordering. So we have a buffer that deals with a part of the buffer that deals with retransmission, and a part of the buffer that is for reordering, and you detect packet loss over here. This picture came directly from the standard. I copied shamelessly. All right. So let's look at performance measurement, packet loss performance measurement. So how well does that work? Okay, I put something together with a network emulator, because then I can control the packet loss, I can control the packet loss, I can control the delay. And we had some test automation using SNMP. And you normally don't do this in presentation because it's a lot of detail. But let me just set it up for you. I'm transmitting a stream. I have a 200 millisecond simulated round-trip delay, and I'm going to drop 1 packet or 5 packets, random loss. And I'm going to change my number of retries. Okay? I set the retransmission buffer to the right number with a little engineering margin. And then I increase the packet loss until it breaks. So, and I will do that multiple times to get a confidence interval. So let's take a look at let's see how this looks like. So I have here the packet loss at which it broke, and here the number of retries. So you want to be underneath here. This is the over my 10 tries. This is the number, the range I got. So you normally want to be operating over here based on your packet loss. And I have another one that's similar for burst losses. By the way, I gave this at BEITC, so it's in the proceedings, and it's also in the Cobalt website if you want to see those plots. Okay, so that deals with packet loss. How do you look at packet loss? Now let's look at packet reordering, because that's something that may happen, right? So how does packet reordering happen on the internet? It's usually when paths change, because the only way a packet can overtake another packet and pass it is only if it went through a shorter path. Otherwise, on an Ethernet, there's no way a packet overtakes another packet. So the question is, if you're not using bonding on multipath, because then it's intentional, right? Is it necessary to accommodate packet reorder? The trade-offs here are this. So if you put a non-zero reorder buffer, that increases your latency, so you're paying with latency. If you put a zero reorder buffer, it's possible, what you may have is unnecessary retransmission, because you saw a gap in the sequence number, you asked for that packet, and oops, it just showed up. Okay? So this question can only be answered with actual internet data. I can go set it up in the lab, but that's not going to tell me anything. It's going to tell me just what I set up. So for that, I resort to literature. There's this very famous paper here where the guys went, they have access to the Sprint backbone, and they measured reordering. You're not going to find this exact table there, because I removed some of the data to show me just UDP packet reorder. And you see that what kind of numbers they get. So on average, for that snapshot, which looked at a fair amount of packets, 500 million packets, the reordering was on the order of 0.3%. So my recommendation based on that is you probably don't want to deal with that. There's an occasional unnecessary retransmission because of that, but it's not a lot. So it's not a lot. Your mileage may vary. He's going to ask me a question about that. So, how do you configure a RIST link? So, what you need to know is, first is the network round-trip time. You need to have an idea of that. You do that with ping. Your application may have a latency bound. What's the maximum latency? You may have that, or you may not have it. And you may know the network loss, or you may not know. Some links have a certain availability number that they give you. So you may know, or you may not know that. So what you're going to configure here, you're going to configure your retransmission buffer, your reorder buffer, and the number of retries. That's what you're going to choose. How do you choose that? So this is what's coming in, this is what I got to choose. How do you choose that? So this is my recommendations for this. If there's a latency limit, you set the retransmission buffer to the latency limit. That's what you can do. And mind you, if you're encoding, decoding, there is also encoder, decoder latency. This is just the latency of the link. You divide the latency by the round trip time. That's your number of retries. As an engineer, I put a margin there. Maybe I add 1. But that's basically what you can do. If there's no latency limit, if you know the network loss, you can look at those plots to give you an idea how many retries you can use. And then you set your network, your retransmission buffer to that number. You basically see how many retries you're going to do, multiply that by your round trip time, and that's what it is. Now, if the network loss is not known, you don't know anything, I'm recommending to start with 4. My friend Adi there wants to start with 7. That's what we wrote in the standard. But I find that 4 works well for me, and he's not going to agree with me with that, but that's opinion. And if your transmit buffer is configurable, you set it as high as you go, because that doesn't add any latency. Some vendors just max it out, and then you don't even expose, which is a good thing. One last thing for you to set up. The reorder, in my opinion, can be set to 0 unless you use bonding. If you're using bonding, you've got to check the differential delay. You've got to characterize the delay between all the paths. And that's kind of very intuitive how to do that. All right, does that work? We did a nice demo at IBC 2018 where 5 companies sent 5 megabits, 8 companies sent 5 megabits per second to banker decoders in Champaign, Illinois. The streams were received by Cobalt decoders. We threw them into a multiviewer, combined them, and sent them to YouTube so people could see that. The streams came from the UK, Canada, Israel, and the US, and many places in the US. And those, important thing to say, those are independent implementations from the specification. We did not share source code, and it all worked. It worked really nicely. You can see here, video flow from Israel, that guy over there did that one. Me, I did that one. And then you have San Diego, Virginia, Massachusetts, Canada, Florida, and the United Kingdom. We did also a pretty cool interop at VidTrans about a month ago. The cool thing about this VidTrans interrupt is that we did more of a mix and match. The IBC demo was all Cobalt decoders, right? At VidTrans, we actually drove decoders there and did a mix and match. And again, we sent streams from all over the world, but now it was a mix and match of decoders. And we also did this. We took a camera in the show floor, and we transmitted the the video out on the internet and then back to the trade show. We had sub 1 second. Yeah. Sub 1 second. Sorry? End-to-end sub 1 second with the encoder-decoder latency. But pretty good. And you can see here, it was a big mix and match. And you see here the very nice-looking people that are part of the RIST group. That guy, the other guy, well, this guy's not here. And our friends from VideoFlow did a bonding demo as well from Israel and France. What's happening in RIST? We are having a fight action, politely discussing about content encryption, VPN, no packet suppression. This is all coming, guys, it's all coming. We had a breakthrough meeting this morning. We actually agreed on something, and the objective is to provide the features to support all the feature supports for internet contribution. We also have a multi-company demo, just like the IBC, running for NAB. If you go to YouTube and look for RIST NAB, you will see something similar to that with the same guys working and streaming. And now, any questions you may have?
Hi. So, any questions for Ciro? So, Ciro, looking at the results that you have, what would have significantly changed them in terms of the internet performance? What are the major underlying factors that would change the round trip delay or things like that?
Well, I'm not sure what exactly you're asking, but one thing that okay, the plots I have were from a very specific packet loss pattern. So the first plot was one packet loss, only one packet lost, IID, which you know the internet's not that. In the second plot, it was a fixed 5-packet burst. Mm-hmm. So different losses will have sort of different results. This is just to give you an idea where you can get. We have people running RIST up to 30–50% packet loss, and it still works. So we have tested with different loss patterns. It always works. Is our question where the plot comes.
Okay. Any other questions? Okay.
A standard internet connection will fluctuate between 1% to 15% packet loss. So that having 4 or 7 retransmission will guarantee you that you can reach the 15% spikes and you can accommodate the 1% easily. So what Ciro did was a very intense testing, and those are the numbers when you do that all the time. But when it spikes, then you can get better results at the same latency.
Okay, thank you.